Welcome, everyone. Today, we're diving into the world of feedback control systems, a fundamental topic in electrical engineering. I'm Rajanikant Metri from Rajaram Bapu Institute of Technology. Over the next few sessions, we'll explore how control systems work, why they matter, and how they shape the technology around us. Let's get started. Today, we're diving into control system engineering. It's a field that's all about designing and managing systems that keep things running smoothly, from simple thermostats to complex industrial processes. We'll explore the principles and tools that help engineers maintain stability, accuracy, and efficiency in these systems. This sets the stage for everything that follows in our discussion. Let's get started. In this session, we're diving into the core of feedback control systems. By the end, you'll be able to translate physical systems into mathematical models, a crucial first step. We'll also calculate time domain specifications for second-order systems and analyze various systems using both time and frequency domain tools. You'll learn to compare different controllers and compensators and apply state-space techniques to understand complex MIMO systems. This foundation sets us up for deeper exploration ahead. Let's take a look at the course structure for our study on control systems. We start with an introduction, covering the basics, the importance of control systems, and key components like sensors and actuators. Then, we move into system representation, exploring transfer functions and block diagrams. After that, we dive into time domain analysis, focusing on system responses, errors, and stability. Each unit is designed to build on the last, giving us a solid foundation over 6 hours per chapter. Before we dive into these units, it's important to have a solid grasp of differential equations, Laplace transforms, signals and systems, and circuit theory. These topics build the foundation we'll rely on. Now, we're covering 3 key chapters. First, stability, understanding how pole zero locations affect it, and tools like the Routh-Hurwitz criterion and root locus method. Next, frequency domain analysis, exploring Bode plots, Nyquist analysis, and how frequency and time domain specs relate. Finally, the state space approach, representing systems in state space, solving state equations, and concepts like controllability and observability. Each unit is designed to give us 6 hours of focused study. For those who want to dive deeper, here are the key references that supported our discussion. We've drawn from classic textbooks by Bode and Nyquist, which lay a solid foundation in control engineering. Additional insights come from Nagarath, Kuo, and Gopal, all respected authors in the field. We've also included online courses from IIT Madras, offering accessible, expert-led material to help you explore control systems further. These resources are great next steps for anyone eager to learn more. Let's talk about why control systems matter. They're everywhere, from the cars we drive to the devices we use every day. Studying them helps us understand how to make machines behave the way we want, reliably and efficiently. It's about mastering feedback, stability, and precision. Whether it's robotics, aerospace, or manufacturing, control systems form the backbone that keeps everything running smoothly. So, diving into this field opens up a world of possibilities. Let's take a look at the industries where control system engineers play a crucial role. From chemical plants to pharmaceuticals, these experts keep complex processes running smoothly. They're also vital in aerospace and automotive sectors, where precision and safety are non-negotiable. Whether it's a PLC or DCS system, these engineers ensure everything operates efficiently and reliably across a wide range of industries. Let's break down some key job titles you'll encounter in control systems. First, the control systems engineer. They handle the overall design, development, and implementation. Then, the automation engineer. They focus on automating processes with tools like PLCs and HMIs. The instrumentation and control engineer specializes in the setup and upkeep of instruments and control gear. Systems engineers take a broader view, often including control systems within larger projects. Commissioning engineers test and start up these systems, while maintenance engineers keep everything running smoothly over time. Each role plays a vital part in the bigger picture. Let's talk about the key skills every control systems engineer needs. These are the tools and abilities that help us design, analyze, and optimize complex systems. From understanding feedback loops to mastering control theory, these skills form the foundation of what we do. We rely on them to ensure systems run smoothly, efficiently, and safely. This slide highlights the essential expertise that drives success in this field. Let's begin with Unit 1, an introduction to control systems. This is where we lay the groundwork for everything that follows. We'll explore the basic ideas behind how control systems work, why they matter, and how they're used in engineering. Think of this as setting the stage, getting familiar with the key concepts before we dive deeper into the details. It's the first step on our journey through the fascinating world of control systems. By the end of this chapter, we'll have a solid grasp on what a control system really is and where you might see one in action. We'll learn how to sketch a block diagram, a simple way to visualize how these systems work. We'll also explore the key features and different setups control systems can take. Plus, we'll dive into why sensors and actuators matter so much. Finally, we'll classify control systems with examples to bring it all to life. Let's start by outlining what we'll cover today. We'll begin with an introduction to control systems, what they are and why they matter. Then, we'll look at the basic block diagram and key components that make these systems work. We'll explore some real-world industrial control examples. Finally, we'll dive into sensors and actuators and explain the difference between open-loop and closed-loop control systems. This roadmap will guide us through the essentials of control technology. Let's talk about control systems, the backbone of how machines and devices manage their actions automatically. A control system is any setup that regulates events or outputs to achieve a desired response. Think about everyday examples: traffic lights directing cars, washing machines running cycles, or thermostats keeping your home comfortable. It's also in advanced tech like cruise control in cars, anti-lock brakes, and even robotic surgeons. From simple switches to complex systems like PLCs and SCADA, control systems keep things running smoothly and safely. Let's take a moment to look back at the historical development behind this project. Understanding where we started helps us see how far we've come, the challenges we faced, the breakthroughs we made, and the lessons we learned along the way. This context sets the stage for everything that follows, giving us a clearer picture of why today's approach matters so much. Let's take a quick journey through the history of control and automation. It all started back in 1769 with James Watt's steam engine governor, an early form of automatic control. Then, in 1800, Eli Whitney introduced interchangeable gears, paving the way for mass production. Over the years, mathematical models and stability criteria emerged, like Maxwell's governor model and the Routh-Hurwitz criterion. By the early 1900s, Henry Ford revolutionized manufacturing with the assembly line. The mid-20th century brought frequency domain analysis, root locus plots, and the first industrial robot. Finally, by the 1980s, advanced methods like robust and adaptive control were shaping the future. Let's dive into feedback control systems. These are systems that adjust their output based on feedback they receive. At their core, they have 5 key parts. First, the input, that's the set value or the target we want. Then, the output, which is the actual process variable we're trying to control. Next, the process itself, what's being controlled. We also have sensing devices that monitor the output, and finally, actuating or control devices that make adjustments. Together, these parts keep the system on track. Let's take a moment to introduce what's coming next. This section sets the stage for everything we'll explore today. It's all about understanding the essentials, the foundation we'll build on together. So, get ready to dive in and see how these ideas connect and unfold. Let's dive into feedback control systems, or FCS for short. These systems are all about keeping things on track by constantly measuring output and adjusting inputs. Think of it like a thermostat. It senses the temperature and switches the heat on or off to keep your room comfortable. Feedback control is everywhere, from engineering to biology, helping systems stay stable and perform as expected. Understanding this concept is key to mastering how complex processes regulate themselves. Now we're looking at a key milestone in our timeline, the FCS, or final certification stage. It's scheduled for the 5th and 6th of May, 2026. This phase marks a crucial checkpoint where everything comes together, and we ensure all standards are met before moving forward. It's the moment we confirm readiness and set the stage for what's next in the project. Now, let's dive into a quick brainstorming activity. We've got 5 minutes to generate ideas around the topic at hand. This is a chance to think freely, toss out possibilities, and explore different angles. No idea is too small or too wild. The goal is to spark creativity and get the conversation flowing. Let's make the most of these few minutes and see what we come up with together. Let's take a closer look at a thermostat as an example within our system. This slide shows how the FCS, or field control system, interacts with the thermostat to manage temperature settings. It's a simple device, but it's key to maintaining comfort and efficiency. By understanding this example, we get a clearer picture of how the entire control system works in real time. Here's an example from the FCS, showing how the data is organized and presented. You can see the key identifiers and dates laid out clearly, making it easy to track and reference. This kind of structure helps us stay precise and consistent, especially when dealing with complex information over time. It's a small snapshot, but it tells us a lot about how the system works in practice. Here, we see a straightforward diagram of a temperature control system. It's an example from the field control system, showing how different components interact to maintain the desired temperature. The diagram helps us visualize the flow of information and control signals, making the process easier to understand. This kind of system is fundamental in many industries, ensuring precision and stability in temperature-sensitive environments. Let's start by breaking down some basic terms we'll use throughout this talk. First, a plant, system, or process is basically a series of steps or activities arranged in order to control material and turn it into a final product. It can also mean any physical thing we want to control, like a robot, a car, or even a classroom. Next, process variables are the physical quantities we track to understand how the process is doing, things like temperature or pressure. Measured variables are the outputs we monitor closely, using sensors to keep everything on track. Manipulated variables are what we adjust to control those outputs. And finally, the reference value, or set point, is the target we want our measured variables to hit. Let's start by breaking down some key terms we'll be using. First, a sensor. It's any device that measures the size or intensity of something we want to control. It detects a physical quantity and gives us an output related to that measurement. Next, a transducer. This converts the sensor's output into a form that's easier to work with, often turning it into an electrical signal. Then we have the transmitter, which sends this signal from the sensor over to the controller. Finally, error. That's the difference between what the sensor measures and the reference value. This error helps the controller decide what to do next. Let's break down some basic terms in process control. First, controllers. They take signals from sensors or transmitters and decide how to keep things within set limits or close to a target value. Then, actuators. These devices respond to the controller's signals by adjusting a variable in the process. Finally, the process control loop. It's all about comparing the actual output to the desired set point, using any difference as feedback to adjust inputs and keep the system on track. Sensors and actuators are at the heart of industrial automation. They help us monitor and control processes with precision. A measurement system starts with the sensor, the primary element that detects changes. Then comes the transducer, which converts one form of energy into another. Finally, the transmitter takes that signal, amplifies it, and standardizes it for further use. Together, these components keep complex systems running smoothly and efficiently. Now, let's turn our attention to sensors. These devices are the eyes and ears of any system, gathering data, detecting changes, and feeding information back to us. Whether it's temperature, motion, or pressure, sensors help us understand the environment in real time. They're essential for making smart decisions, automating processes, and improving safety. In this part of the presentation, we'll explore how sensors work and why they're so important to our project. Sensors are devices that detect changes in the physical world around us. They respond to inputs like light, heat, motion, or pressure, anything measurable. When they sense these inputs, they convert them into a usable output signal, which could be electrical, mechanical, or magnetic. Essentially, sensors translate real-world conditions into information we can use, making them essential for countless technologies we rely on every day. Let's talk about sensors, the unsung heroes of industrial automation. Sensors detect and measure physical properties or events, then turn that information into signals machines can understand. For example, proximity sensors tell us if an object is near or not, using methods like induction or ultrasound. Temperature sensors keep a close eye on heat levels, which is vital for processes that depend on precise temperature control. Together, these sensors help keep everything running smoothly and safely. Let's talk about sensors, the unsung heroes of modern industry. Pressure sensors keep things safe and efficient by measuring pressure in all kinds of processes. Flow sensors track how fluids or gases move, helping us control everything with precision. Level sensors tell us how much liquid or material is in a tank, so we never run empty or overflow. Position sensors track movement and location, which is crucial for automation and robotics. And vision sensors. They use cameras to see, inspect, and guide, making smart manufacturing possible. Let's talk about actuators, devices that change something physical. They take electrical signals or electricity and turn them into mechanical energy. That means they can create motion, like moving a robotic arm, or cause changes in the environment, such as opening a valve or adjusting temperature controls. Actuators are the muscles behind many machines, making things happen when we send the right signals. Let's talk about actuators, the workhorses that turn control signals into real-world movement. They take electrical or digital commands and convert them into mechanical motion, making industrial automation possible. There are several common types. Electric motors drive conveyors and pumps. Pneumatic actuators use compressed air for quick, precise moves. Hydraulic actuators handle heavy-duty tasks with high force. Solenoid valves control fluid flow by opening and closing passages. And servo motors provide exact control for robotics and CNC machines. Each plays a vital role in keeping processes running smoothly. Let's talk about sensors and actuators, two fundamental components in many modern systems. Sensors detect and measure physical things like temperature, pressure, or light, then convert that information into electrical signals. Actuators do the reverse. They take electrical signals and turn them into physical motion or force, like moving a motor or opening a valve. Together, they're essential for monitoring environments and controlling devices, especially in the Internet of Things, where remote data collection and system control go hand in hand. Let's talk about the advantages of feedback control systems. First, they help reduce nonlinear effects, those tricky behaviors you often see in open-loop setups without feedback. They also cut down on external noise and disturbances, making the whole process cleaner. With feedback, we boost efficiency, accuracy, and overall quality. Instability and uncertainties shrink, and we gain precise control over transient responses. Plus, feedback systems improve gain and bandwidth, giving us a stronger, more reliable performance. Now, let's dive into the heart of our discussion, the EV production line within an advanced, automated smart factory. We'll explore real-world examples of industrial control systems that power this transformation. These systems are the backbone of automotive manufacturing today, driving efficiency, precision, and innovation. As we move forward, keep in mind how these technologies aren't just concepts, they're active, shaping the future of how electric vehicles are built. Let's take a closer look at robotic assembly lines in automotive manufacturing. These systems are a prime example of industrial control in action. Robots work together seamlessly, handling tasks with precision and speed that humans can't match. This kind of automation boosts efficiency, improves quality, and keeps production running smoothly. It's a perfect illustration of how industrial control systems transform complex processes into reliable, repeatable operations. Let's look at some examples of industrial control systems in action. Here, We have speed control, the kind of system that keeps machines running at just the right pace. Then, there's ignition control, which manages the precise timing needed to start engines or processes safely and efficiently. These examples show how control systems are the unseen hands guiding complex operations every day. Industrial control systems are everywhere, powering a wide range of applications. In industry, they keep robots and assembly lines running smoothly. In the military, they guide tanks and missiles with precision. They're essential for exploration too, whether that's on new continents or far-off places like the Moon and Mars. Transportation relies on them in cars, ships, and aircraft. And in our daily lives, they quietly manage devices like washing machines, boilers, and air conditioners. These systems shape much of the world around us. When we talk about industrial control systems, there are two main types to keep in mind. First, open-loop control systems. These operate without feedback, meaning they don't adjust based on the output. Then, we have closed-loop control systems, also known as feedback control systems. These constantly monitor their output and make adjustments to stay on target. Understanding the difference between these two is key to grasping how industrial processes are managed and optimized. Let's talk about open-loop control systems. These systems don't monitor their output to adjust their actions. The output isn't measured or compared to the input. The controller simply acts without feedback. Because the controller's decisions don't depend on the output, these systems are simpler and have fewer parts. That makes them ideal when you don't need precise control or fine-tuning of the output. They're straightforward, reliable, and get the job done where precision isn't critical. Let's talk about closed-loop control systems. These are systems where the output actually influences the input, creating a feedback loop. This feedback helps the system maintain the desired output, even when disturbances try to throw it off. Unlike open-loop systems, closed-loop systems automatically adjust themselves. That's why they're often called automatic control systems. They keep things steady by constantly correcting themselves. This feedback mechanism is what makes them so reliable and efficient. Let's talk about drying control systems, focusing on the difference between open-loop and closed-loop control. An open-loop system operates without feedback. It follows a set process regardless of the outcome. Closed-loop systems, on the other hand, constantly monitor results and adjust accordingly. This feedback loop makes closed-loop controls more precise and responsive, especially in processes like drying where conditions can change. Understanding this difference is key to improving efficiency and product quality. Let's talk about temperature control systems, focusing on the difference between open-loop and closed-loop control. An open-loop system acts without feedback. It simply follows a set command, no matter what happens. In contrast, a closed-loop system constantly monitors the temperature, compares it to the desired value, and adjusts accordingly. This feedback loop makes closed-loop systems more accurate and reliable, especially when conditions change unexpectedly. Understanding this difference is key to designing effective temperature controls. Let's talk about numerical control systems, how we use numbers to guide the motion of machine parts. There are two main types: open-loop and closed-loop control systems. Open-loop systems follow commands without checking if the motion actually happened. Closed-loop systems, on the other hand, constantly monitor and adjust based on feedback. This example shows the difference. Open-loop moves blindly, while closed-loop keeps everything on track. It's a key concept in precision and automation. Let's take a closer look at material testing systems by comparing two types of control: open-loop and closed-loop. An open-loop system operates without feedback. It follows a set input without adjusting to the output. In contrast, a closed-loop system constantly monitors the output and makes real-time adjustments to stay on target. This example highlights how closed-loop control can improve precision and reliability in testing materials. Understanding this difference is key to choosing the right approach for your application. Let's look at some examples of closed-loop control systems in action. One common example is motor control, where the system constantly adjusts to keep the motor running just right. Another is cruise control in cars. It senses your speed and makes tiny changes to keep you steady on the road. These systems are all about feedback, using what's happening now to guide what happens next. It's a smart way to stay on track, no matter the conditions. Let's explore the key differences between open-loop and closed-loop control systems. Open-loop systems don't use feedback. Their control action runs independently of the output. This makes them simpler, faster, and cheaper to build, but less accurate and reliable. Closed-loop systems, on the other hand, rely on feedback to adjust their actions. They're more complex and costly, but offer greater accuracy, stability, and optimization. Examples help bring this to life. Think of a traffic light for open loop and a refrigerator for closed loop. As we wrap up, here are the key references that supported our exploration today. These sources range from foundational texts on industrial control systems to comprehensive introductions and practical examples. They provide deeper insights into control, engineering concepts, and applications. If you want to dive further into this topic, these materials are a great place to start. They've helped shape the ideas we've discussed throughout this presentation. Here, we have a comprehensive set of questions designed to deepen our understanding of control systems. They start with the basics, defining what a control system is, and distinguishing between open-loop and closed-loop types. Then, we explore the key components, sensors, and actuators, and how they fit together in block diagrams. Later questions invite us to analyze real-world examples, like water level management and home automation, and to compare the strengths and weaknesses of different control strategies. This list guides us through both theory and practical application, reinforcing core concepts step by step. Thank you all for being part of this journey today. I appreciate your time and attention. Let's take what we've explored and keep pushing forward together. Looking ahead, there's so much more to discover, and I'm excited to see where we go next. Thanks again, and take care. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.